Welcome, everyone, to Lecture 11 of Module 2 of the course Ecological Economics. In our last lecture, we examined abiotic resources, the non-living foundations of the economy, and today we turn to biotic resources, the living ones. And we will see that they introduce a quantum leap in, complexity, makes it even more complicated, actually. Okay, so first let's take an overview of what is biotic resources. Let me give you the big picture. So biotic resources are living resources that provide raw materials, life support services, and waste processing. And all of them are, ultimately powered by solar energy, something which we discussed in our last lecture, that solar energy actually is one of the most significant resource that we have. As non-renewable abiotic resources are gradually exhausted, society will depend ever more heavily on self-renewing capacity of biotic resources. So understanding them is not merely an academic exercise, it is essential preparation for the economy of the future as well. Now here is, what makes biotic resources fundamentally more complex than abiotic ones. A fossil fuel deposit, if you remember, we discussed, is simply a stock. A mineral ore is also stock, but biotic resources, which is forest, fishery, wetland, is simultaneously a stock and a fund. It provides raw materials and ecosystem services at the same time. So if you overuse them, it affects both. You also use forest as a resource, and it also acts as a fund for you, right? Because it has the capacity to absorb CO2, for example. That duality is what makes the analysis so much richer and the policy also so much difficult or harder. We can organize biotic resources into three categories. First is renewable resources, elements of ecosystem structure that provides raw materials like forests, fisheries, crops. These are all renewable resources. These are stock flow resources as well. They are rival and exhaustible if overharvested. Second is, so the first characteristic is renewable resource. Second is ecosystem services. That means the functions that ecosystem performs for human emerging from interaction of their structural elements. These are fund service resources. They are largely non-rival and impossible to stockpile. And third is the waste absorption capacity. So renewable, second is the services that they provide, and third is the waste absorption capacity, the ability of ecosystem to proceed and neutralize our waste. This is also a fund service, but it differs from other ecosystem. It is rival too, because if one country uses it more, for example, the whole problem of carbon dioxide emission is that if I am reducing my emission but somebody else has increased, then the capacity of the atmosphere overall comes down. So it is rivalrous as well. Because of this important distinction, we treat waste absorption capacity separately, even though it is technically a subset of ecosystem services. Okay, moving on, let's try to simplify this further. So first is ecosystem structure and function. Let's understand this whole ecosystem in a bit more detailed way. So what is an ecosystem? Ecosystem, particularly structure, refers to what an ecosystem is made of. The individuals like us, the communities of plants and animals, their age distribution, their spatial arrangement, and the abiotic resources, soils, water, minerals, that are the part of the system. Conventional natural resource economics has traditionally focused almost entirely on structure, treating ecosystems as stock of harvestable material. So like timber volume, okay, fish biomass, crop yield. But this focus on structure alone misses something really profound. So what is that is they are missing out the function that ecosystem provides. So this is basically what an ecosystem does. The emergent phenomena generated by interacting these structural elements. So these are properties of the whole that cannot be predicted from any knowledge of the part that taken individually. So for example, energy transfer, nutrient cycle, gas regulation, climate regulation, these are the functions that ecosystem provides. None of these properties of any individual organism. So they emerge from the system as a whole. So it is not that climate regulation is a standalone property. Climate regulation, water cycle, nutrient cycle, all of these are a whole and emerge from an ecosystem as a whole. So Daly and Farley offer a very interesting illustration of this. So consider the Amazon or the Congo basin. Each individual tree taken alone has very little impact on climate or nutrient cycle. If you take only one tree, but bring hundreds of millions of them together in an interacting system, and then something very different emerges, something far greater than the sum of its part. So for example, Amazon forest canopy filters 98% of sunlight at ground level. It traps air, maintains constant humidity, high humidity. Its trees absorb storm energy and aerate the soil. The forest generates up to 50% of its own rainfall through evapotranspiration. It absorbs up to 90% of solar energy that strikes it. None of these properties belongs to any single tree. They belong to the entire Amazon forest system. So that is why it is actually the entire system, the entire Amazon forest system or forest canopy regulates world's, Earth's atmosphere. This leads also to a critical and sobering conclusion that loss of structure leads to degradation of function. So if you lose the structure, it will also degrade the function that the ecosystem plays. And because these functions are emergent, arising from complex, interaction, that degradation can actually trigger positive feedback loop that may be entirely irreversible. You cannot easily, for example, rebuild an Amazon by replanting trees. That's very important. Just going ahead and we are chopping off a lot of trees and we are replanting 10 does not really rebuild the entire system. The system's complexity built over millions of years of co-evolution really cannot be, reconstructed on human time scale. So this is an important point, and many of us during Environment Day go and do a lot of replantation while we keep on degrading a lot of these important canopy. It's a very important concern, because these were not just built overnight. These took millions of years to come up. So over 2 days, by planting few trees, we can never get back the entire system. And because what matters is the system as a whole, not just one or two tree. Now next, let's look at renewable resources, sustainable yield. So the key insight is that biological stocks can replenish themselves, but only if we harvest them more slowly than they reproduce. So everything has a capacity to replenish. So this is why we call it as a sustainable yield. But that yield has to be, it is only possible when you are not, or you are giving them enough time to replenish. So, this is captured by the concept of yield curve. So first, let me walk through the key points of that, curve. Carrying capacity is, actually denoted by K, as you see on the figure. It's the population level at which average death rates equals average birth rate. So the natural equilibrium of an unharvested population. At carrying capacity, net growth is zero. So interestingly, if we start at K and begin harvesting some individuals, like some fish, some trees, we actually increase productivity because the remaining individuals have more resources now available to them. So it's an important point. Initially, when you are taking away some fish, some trees, we are actually improving the productivity, increasing productivity, because they have now more space. So that's why you see the curve going up. It reaches a peak of the yield curve, maximum sustainability yield, the greatest harvest that can be removed indefinitely under existing condition. It sounds like the ideal management target, but there is a critical caution. The maximum sustainability yield varies dramatically from year to year. Say, for example, if there is an El Nino event, predator cycle, pollution load, temperature changes. So science simply cannot really estimate accurately enough to set that quota, how much would be the maximum sustainable yield. That's why MSY, or maximum sustainability yield in theory, often therefore leads to overharvesting in practice. The most dangerous point on the curve is the critical dispensation point, the minimum viable population. Below this threshold, death rates exceeds birth rate. So initially you had more, death rates equal to average birth rate. Now you reach a stage where death rate exceeds birth rate. So when I'm saying, death rates equals average birth rate, it means that while you are extracting them, there is also an average amount of birth rate which is taking care of the death rate. But when you reach a stage where your death rate is higher than the birth rate, even in the complete absence of harvesting, the population actually enters spontaneous self-reinforcing decline. The tragedy is that we rarely know where this point is until a population has already crossed it. The same dynamic applied to forests. Clearing some trees initially speeds the growth of the remaining forest because there's more light, more water, more nutrients becomes available, and space opens for seedlings. But beyond a certain point, the seed source becomes too distant. Soil nutrients are lost. Trees of the same species are too far apart to even cross pollinate effectively. So then sustainable yield begins to fall, just as with the fish population. Even if you are not doing anything, it will start falling because they cannot cross pollinate any longer. The key relationship are simple to state. If harvest is less than sustainable yield, the stock increases. If harvest equals sustainable yield, the stock remains same. If harvest exceeds sustainable yield, the stock declines. And if the stock falls below critical dispensable point, even reducing harvest to zero cannot save the pollution without active intervention. So in a way, if you look at it today, we say that we are making all effort to reduce CO2 emission. I mean, if we say so, that we are, but still the amount of CO2 which is already accumulated will take another decades or maybe 2 decades to actually reduce the temperature the way we want it, because we already have crossed the critical dispensation point. Okay, now let's look at ecosystem services, which we already discussed a little bit, but a bit more to give you a better understanding. These, from the point of view of stock and fund, these are fund services generated by ecosystem structure. So remember, this ecosystem structure and ecosystem services are very closely connected. If you do not preserve the structure, your services obviously will not be there. But what I was trying to say is that the resource economics focuses mostly on the structure and not connecting it to the services that structure provides. Now, these structures are largely non-rival, non-excludable, and without substitutes. Okay, that's the biggest problem. If I am doing something with one tree, it seems to be non-rival. Nobody can stop me also, and there is no substitute for that tree as well, like one which has come up with millions of years. What makes ecosystem services so distinctive and so challenging to incorporate into economic analysis is that they are emergent phenomena. They arise from an interacting structural elements of ecosystem, not from a single component, like I had mentioned. You cannot point to any particular tree or microorganism and say that that is the climate regulation service. It is a property of the whole. So one cannot tell you anything. Because they are fund services, they cannot be stockpiled. You cannot save up last year's flood regulation and use it next year. You cannot bank the pollination service of a forest and draw on them during a drought. The service is provided continuously at a rate fixed by ecosystem structure or not at all. So the best illustration of how replaceable these services are again comes from an experiment called Biosphere 2 conducted in actually Arizona. At a cost of $200 million, Edward Bass and his team attempted to replicate ecosystem services sufficient to sustain just 8 people in a sealed artificial environment. The project failed. 8 people, $200 billion. The actual global ecosystem sustains 8 billion people at effectively zero direct cost. Just imagine. The implication is therefore profound. And if we had to replace natural ecosystem services with engineered substitutes, the cost would be basically infinite. So, let me also briefly, survey the main ecosystem services provided by forest, drawing from this table. So basically, so this has been drawn from Daly and Furley's book. When you look at that book in the textbook, you will see this table as well. So you see gas regulation, you can see what activities it does, carbon store carbon dioxide, etc. Climate regulation. I'm not going to go into each of them. Then you also have water regulation, you have erosion control, you have nutrient cycle, biological control. All of these, most of these services are non-rival. You benefit from flood regulation. Your benefit from flood regulation does not reduce, mine. Most of them are non-excludable. No institution could feasibly prevent someone from benefiting, for example, from atmospheric gas regulation. So these two properties, which is non-rival and non-excludable together, explains why market systematically fail to account for ecosystem services. So in one of the last lectures, I spoke about market failure. If that wasn't clear at the time, so this is exactly what we mean. Since I cannot ask or exclude anyone, or it is non-rival, it is, you cannot charge anyone for what you cannot exclude from, and you cannot also allocate anything because it is non-rival, right? This is precisely why ecological economics talks about policy must go beyond market mechanism. Does it mean that because there is no market which shows how important these services are, for example nutrient cycle, we should not bother about it just because there is no market value? Okay, now, as I mentioned, that waste absorption capacity is a third category of biotic resources, and it very deserves a special attention because it illustrates with unusual clarity what happens when a fund service is exceeded. Something we did discuss about, but let me just again make it a bit more explicit. So here is the key is, asymmetry to keep in mind. We control faucet, the rate at which we generate waste, but we do not control the drain. Okay, the rate at which ecosystem can absorb it. Suppose we decided that, okay, we will, at the rate at which we will generate the waste, we will recycle some, we will put some technology to, reduce the waste generation, but we cannot control at what rate whatever is getting generated, the ecosystem can actually capture it or absorb it. So that absorption rate is already fixed by ecosystem structure. Exceed it and the system begins to therefore degrade, and once you have degraded the system, you have pushed it so far, your system will collapse, and even if you now decide to reduce your waste, it merely doesn't help. Waste absorption is a fund service. It occurs at a fixed rate that we cannot meaningfully increase in short run. But unlike most ecosystem services, waste absorption capacity is rival. If I discharge pollution into a river, I reduce the river's remaining capacity to absorb yours. So this rivalry is what makes waste absorption a distinct and particularly a policy relevant category. So that is why you do see that, there is, water cess, there is wastewater treatment plant, because to some extent, it seems that it has a rivalry component. If one industry is polluting a lot, it is actually degrading the capacity of the river as a whole. Somebody who is using this water for some other purpose cannot use it anymore, right? So just let me just, walk you through an example. For example, to a lake, as pollution increases, what happens to a lake when pollution basically increases? So a progression that is, kind of tragically familiar in many parts of the world where lakes get a pristine lake, wastes are heavily diluted. So the ecosystem absorbs them initially with minimal impact on its functioning. But as pollution increases in the early stage, higher waste loads cause bacteria and algae to thrive. Exactly what I showed in the sustainable yield curve. They are possessing the additional material. But even at this stage, fish begin accumulating toxics, and sensitive species begin to disappear. So, initially, okay, there was a capacity. Eventually, the pollution causes so much of bacteria and algae to thrive in that river system that many of these sensitive species, they start disappearing. With heavy pollution, the water becomes also unsuitable for drinking even after treatment. Excess nutrients cause, eutrophication, algal blooms proliferates on surface, and when they respire at night, absorb all oxygen in water. So because it absorbs all the oxygen in water, fish and others cannot survive, they die out. right? Finally, at the point of system, it kind of collapse. Even if the algae you have removed, you have cleaned it, waste actually accumulates faster than anything can process it, further degrading the remaining biological community. The waste absorption capacity of the system is destroyed. Restoring it requires an extraordinary way of restoring the capacity of the system, right? In some cases, it is in fact impossible. One interesting example that I want to give you is that Ganges, which is a river flowing through in India, is known to be something that it has a very high capacity to assimilate waste. But today, what you see is that we reach the level that even till date, when we are talking here, we are yet not able to bring back that capacity that Ganges had. We have so many programs of cleaning Ganges, but we are yet not able to clean it the way we would like it to be cleaned. So this is exactly what is important to remember, that ecosystem essentially have essentially zero adaptive capacity to absorb these materials, which is why even small quantities can lead to disproportionate damage. Okay, now let's move on to the biotic resources, a summary comparison. Let me bring the three categories of biotic resources together in one and as a key takeaway. So if you remember, we started that I mentioned that the biotic resources, first, remember, they are renewable resources and they are stock flow resources. They're excludable and rival within a generation. Whether they are rival between generation depends entirely on the rate. So you can make it, actually we have already made it, unfortunately, between generation as well. And so that is why we are so much talking about sustainable development and sustainability. If harvested sustainability, future generation inherit the same stock. If over harvested, the stock is diminished or destroyed. Substitutability is high at the margin. We can often switch from one timber species to another, or from fish to other protein sources, but ultimately these resources are non-substitutable as basis of material production. So you may not eat this fish anymore, you might eat another, because both is giving you a protein source, but you cannot get back the fish which you have lost. Ecosystem services are fund service resources. They are non-excludable and largely non-rival. The services are available to all, and one person's enjoyment does not reduce another's. So they are non-rival between generation as well, provided the ecosystem structure that generates them remains intact. Substitutability of ecosystem services is very low. As I discussed in Biosphere 2 experiment, it demonstrated that engineering substitute for natural ecosystem services is essentially impossible at a realistic scale. It couldn't do it for 9 or whatever the number I mentioned. It could not. Imagine how large a population it sustains. Now, the last one, which is waste absorption capacity, is also a fund service, but unlike other ecosystem services, it is rival. And if one is polluting, it makes, whether it is rival between generation, of course, depends on again the rate of waste inputs within the absorption capacity. But ultimately, do remember that absorptive capacity of the biosphere is non-substitutable, and I have given you the example of Ganges as well. So the three key takeaways that tie all of this together, that first, humans depend entirely on plants to capture solar energy. You and I cannot capture it the way plants does it, directly as food and fuel, and indirectly through ecosystem life supported that plants generate. No substitute actually exists for these functions at a plausible rate. Second, every act of economic production depletes ecosystem structure, which reduces ecosystem function and the services that function provides. Growth is not free. It has a structural cost that conventional economics ignores. So when I kept saying that you do not grow in void, this is exactly what happens. But it depends how far you want to take it. Third, every act of production generates waste. That waste directly harms well-being when it accumulates, and it further degrades ecosystem function. The sink fills while the source depletes, and both processes compound each other. So makes it more complex, both source and sink. Okay, finally, what is the big idea from this lecture 11? Let me close by bringing this together, as I have already mentioned, so I'm going to keep it short. The first is the relationship between ecosystem structure and function. Do remember that there is a strong relationship. If you degrade the structure, it will also degrade the function. Second is the stocks and funds duality. Biotic resources are simultaneously stock providing raw materials flows and funds to generating ecosystem services. So if you overuse them, it will reduce both the stock and the fund function at once. Third is the limits of maximum sustainability yield as a management concept. Many people bring this MSY curve as a very powerful pedagogical tool for understanding the relationship between harvest and population dynamic. But it is not a reliable management tool because, MSY varies annually with ecological conditions, and science really cannot estimate it accurately enough to set annual harvest quotas. It's very difficult to, rule over nature, to be honest. And the fourth is the rival rate limited nature of waste absorption capacity. I'm not going to repeat this. We already discussed that there is a capacity and there is no substitute for that waste absorption capacity. And the fifth, perhaps the most important of all, irreversibility and ignorance, meaning extinction is irreversible by definition. Ecosystem collapse is often effectively irreversible on any human time scale, and we frequently operate under conditions not merely of uncertainty but of ignorance. It is not, we keep saying there's a lot of uncertainty, but more than uncertainty, we do not even know the range of possible outcomes in the face of irreversibility and ignorance. One is that it is irreversible, another is ignorant. The conservative principle is not therefore timidity, it is a rationality that we need to have a conservative principle. So this is something to keep in mind. Both the biotic and abiotic natural resources have, again, like I had mentioned, within the resources of biotic and abiotic, there are different ways of looking at them. They are so distinct, they are different from each other, and therefore we need very different policy toolkits to take care of them. So I'm going to stop here for today. In our next lecture, we will begin to look at how these ecological realities should shape in macroeconomic framework. So I'm going to stop here. Thank you.